Hello students, so my name is Rishabh Anand and Physics faculty at Perfect Academy. So today we are going to start our chapter rotation and in that moment of inertia. Before that, if you know the term inertia in kinematics means that it's the inability of a body to change the state of its rest or motion, right? So here, first after that we look at rotation part. See, this comes in the section of rigid body. And what is definition of this body is that the distance between any two particles, like distance any two particle inside of that bigger mass will always remain fixed. Okay, that means this d will remain fixed. Okay, if that distance d between any two particles is not changing, then they are called rigid body. Okay, in the same case, like if you translate it, right, like if a block is there and here this part and this is moving with some v velocity, right, and if I take a bigger block, say these two parts are there. Okay, this block is moving on a frictionless or any friction surface, they are moving. So that means if this distance d is to be a constant, then that means velocity of a should be equal to velocity of b, right? Or now if something you say that these two are the part or point inside this mass, right, and say that this is having some velocity v here and this is having some velocity vb here, okay, at some, say at some angle theta, okay, like this. Now see, if you see this component of velocity, this has two components along this and along that one, right? Now this also has this component and that component, right? So these two component, okay, these two component, this and this, these two, say VA1 and VB1, okay. Now these two component, when you see as respective velocity of B with respect to A, then you will write velocity of B then velocity of A1, right? That means with respect to A, if you fix this point A here, then that means this seems like moving around, right, at distance d. If you fix here, that means this is here and this man is seeing this B as moving like this, okay, but this d is always fixed between A and B because this body is rigid body, right? So this can be considered as a circle, a circular path where one is standing at the center and another particle is moving, right? A is at the center and B is moving, and this is the d distance between them, right? That means with respect to A, B is going in a circular motion, but the point is this d remains same, right? Here d remains same, okay. Then we can say that for a rigid body, distance between two particles are fixed. Then that particle, either they go in translation or they go in a circular motion, right? These two are the conditions possible when you take two particles for any rigid body, right? So from there rotation comes, right? This is fixed and this is watching this person B going in a circle, right? Now after that, so definition of this rigid bodies are important to know that how the rotation comes, right? Now if I say a body is there, right, a body is there, and if I clamp that body here, you can write a part of hinge, right, or you can say pivoted, right? So if a body is pivoted here at this point, right, so I take here some point M here, Inside that, this is bigger mass m, and this I take distance d between that. Okay. Now, if you make it fall, like, right, it will fall like this. Like if I'm doing this duster here and here I am clamping it, so this will go in this motion, right? That means this will come somewhere here after going in a circular motion after some time t, right? Okay. As this part of the block will fall, it will have some omega, which is angular velocity, right? So each and every part will be going in this circular motion and they will have same omega, right? That means you can say this has a tangential velocity of omega into d, right? This mass m has tangential velocity of omega into d, because you know that v is equal to omega r, right? Now, when you write kinetic energy for this mass, right, then you write half m v square, which is half m omega d whole square, which is half omega square md square, right? Now you can also write for each and every mass. If you say small mass dm at any point inside this mass, for dm mass you can write small kinetic energy as half dm, say r square and into omega square, right? This part, okay, this part you can imagine as in the kinematics motion serve as mass, and this as serving for velocity, right? This is for rotation part and this was for linear, right, linear motion. So this also you can draw a analogy from here, and this rotation, that is called pure rotation, and that is done only when you pivot and hinge it, right? So this is called pure rotation part. So this dm r square, this is termed as moment of inertia, okay, moment of inertia, and that is what you say the inability of a body to change the state of rotation, right? Like if I give you example, suppose here I'm clamping it here, this marker, okay, so now I can rotate like this, right? I can rotate like this, okay, this is rotating about this axis, okay, but suppose instead of this marker there is a bigger rod, okay, and that bigger rod is too heavy that simply you cannot just rotate it, right? Simply if this is a marker I can rotate, but imagine with the bigger rod, much more bigger rod, and this is the axis rotation, okay, so it will be difficult for us to rotate, right? So this moment of inertia you can say is proportional to mass of a body, right, and also distance, right, that r, simply proportional to r. R is the perpendicular distance from the axis, which axis we are taking to rotate, right? Okay, if I take the middle axis, that this means this is the axis and this marker is going like this in and out of this axis, okay. So each and every mass m and that r perpendicular distance from the axis, which you can say that perpendicular distance from axis, which you are choosing, right? Axis can be anywhere. If you want to clamp this or pivot this mass m somewhere here, then again for this mass m, this distance, say d1, will change, right? So that perpendicular distance will change. So we say that moment of inertia finally we conclude as given as moment of inertia as m r square, okay. Now we'll take some examples. See. Okay. Let's take this axis and a mass m here having distance r, okay. So this mass m. So you want to rotate this mass m about this axis. So you, for this you will write moment of inertia as mr square, right? Now, since moment of inertia depends upon mass, and mass also depends upon density of the material, so finally we can say that moment of inertia depends upon density also, and also size matters, size of body.